So let's see if we could explain exactly why. The first part of it is not that surprising. It is exactly the definition of a derivative. The limit as x goes to c of the function. In this case, it's the product minus the value all over x minus c. This is a secant slope. Slap a limit on it, turns it into a tangent slope. The key to it, or one key to it, is taking this brilliant step, amazingly creative, and comes sort of out of nowhere. That's why it's so amazing. I'm going to leave some space here for the incredible step here, x minus c, and then I have minus g of c f of c, right? Here's the amazingly creative step. You do is you add some crazy stuff here. You actually subtract and you add some stuff. This is a famous idea. The idea of adding something that's equivalent to 0. That goes, we've done that many times. We're about to do it again. I'm going to subtract here f of x times g of c. And if I stop there, it would be totally illegal. But if I add it back, I added back f of x plus or times g of c. What I've added is I added an fx g of c and then I subtracted it, so this is a total of 0. I know, huh? It's crazy. How do you even think about doing that? But people did. And then you separate this into two separate little integrals. You say, all right, this is equal to, I'm going to need some more room, so I'm going to make these lines thinner. This would be the limit as x goes to c of g of x times f of x minus f of x g of c all over. Can you guys see that? Oh, you might need to be zoomed in. You guys want to zoom in? Just a little bit. There you go. All over x minus c, and then plus, I'm going to separate this into two fractions, and then I'm going to distribute the limit. The limit as x goes to c of f of x g of c minus g of c f of c all over x minus c. That's that fraction. The f of x g of c, all that over the denominator, and that's that fraction over the same denominator. That's this fraction, and this one over here would be that one. Okay? If I added the two fractions together, you'd get exactly the same thing from above. Alright, let's see if you can see. Alright, and then you could pull out an f of x here, and you could do that. Let me switch back to my thin line so we can have ample room here. You could do this if each one exists and is finite. That was one of the limit properties. I could call this f of x times the limit as x goes to c of g of x minus g of c. Can you see that? I pull out this f of x. See that f of x, that f of x? That one pulls out, and so I could distribute the limit, and that becomes x minus c. Instead of having the limit of the product, I have the product of the limits. Okay, this f of c comes right out, but because it has an x, you still need a limit on there. And then that becomes plus, I'm going to play the same game here, but here I could pull out, I'm going to no. See that right there, the g of x, g of c and g of c, I could pull that out. That one doesn't even have any x's, so I don't even need a limit. If I pull the constant, let's go back to my thin line so we can squeeze everything. I have ample space there. It'll be really clean if we do it this way. So I could pull out the g of c. That's pulling it out, and that would leave in there the limit as x goes to c of f of x minus f of c all over x minus c. Stop me if I'm lying. But wait, there's more. Let's do this piece right here. What is the limit of f of x as x goes to c? Well, this is one of the important ideas, and we'll have it as part of the homework, but if the function has a derivative, which is a premise for all these properties, the function must have a derivative and be finite. Then the function is continuous, and one of those three conditions that it meets if it's continuous is that all you got to do is plug it in, and so this would give you f of c. Because it has a derivative, it's continuous, and because it's continuous, it meets those three criteria, one of which is that the limit is equal to the value of the function. That takes that part, that takes care of that piece. This piece right here looks incredibly famous. The limit of g of x minus g of c all over x minus c. That's the secant slope for g, and that is the secant slope turned into a tangent slope. So this becomes g prime of c. Yes? That takes care of that. Then you go on to here, g of c, and then what does this become? This is incredibly famous. This would be f prime of c, the derivative. And now I can say yippee-ki-yay. Right there, there's my incredibly famous property, the derivative of the product. Let me zoom you out of here. Let's get a wider view, not too wide. There. This is sort of a yippee-ki-yay, because now I've got here the derivative of the product is equal to the sum of each one, where you take the derivative of one on the first part and the derivative of the other one on the second one. Proven, delivered. They call me the mailman because I deliver. And then, of course, the next thing you want to do is talk about quotients. Quotient of functions. So if you have, if you have g of x and f of x on the bottom, how would one take the derivative? But I think I'm tired for now, and I think this is about the right length for the video. So I think we should call it a day here, and try to get a view of the big picture. We want to study all sorts of functions, and today we invited a mix of it. We want to do not only famous functions, but we want to do famous properties. I think we did 2 or 3 of the day. Pulling the constant, the derivative of the sum or difference, and the product. That's 3 properties. Next time we will do 2 more. We will do the quotient, and we will do something super famous called the chain rule. Okay, guys, it's been fun. I think we should wrap it up. What do you guys think? It's fun. See you guys next time. Practice your derivatives. Peace. Alright, so I was saying that in practice what you do is you look at the 2 and you say, okay, the 7 is not going to matter, so I'll just bring it down. But then you imagine 2 times 7 is 14. You subtract 1 from the 2, that gives you 14x. The principle behind it, of course, again, is just pulling out the constant. Maybe we do it one more time here on a famous one. If you have 5 times sine x, the principle is that you could take this 5 and not even worry about it. Leave it out of the derivative business and just worry about the derivative business here. And of course, the derivative of sine x is cosine x. Oh, this was a nice problem last time, and hopefully you did something like that for homework. Super famous. And that's so the constant is pretty easy. You just don't even worry about it. You figure out the derivative of the function and then put the constant later. So in practice, when people have 5 sine of x and you got to take the derivative, people don't even worry about the 5. They just write the 5 over and they take the derivative of the sine is cosine x, and that's how you get the derivative of 5 sine x. Again, the principle is that the 5 does not affect it. You could pull it out of the derivative business. Clear? One more or no? That's enough? Let's practice some famous ones. Why not? You only live once. Let's practice some of the timeless ones. Again, the 9 can be pulled out of the derivative business, and this becomes 9, and the derivative of ln x is famously 1 over x. So you just have 9 over x. Okay? Super duper famous. Alright, and this is the principle. And of course, there's always 2 famous questions. One is how do you actually apply the principle? And the other famous question, the one I find most fascinating, is why? Why? In fact, that's the part that humans find fascinating. We're all wired to love to ask why. My little kids always ask why. Puppy, why doesn't Spider-Man have guns? Why does he have spider webs? Puppy, why this, why that? We stop asking why when we grow up, but we want to ask why here. We don't want to stop asking why. Why is it that you can pull out the constant? Here's a simple proof, or a sketch of a proof. One way to look at it is forget about it. Suppose you didn't know what to do with that, right? Suppose you just wanted to find what that is. You would go on and use the solid stuff that we learned, that would be the definition of the derivatives. This would be the limit as x goes to c of k f of x minus k f of c all over x minus c. And then you say, well, that would be equal to the limit as x goes to c. I could factor out a k here. Out of these two, k, see this k right here, k and k? I could factor it out using the distributive law, and that would leave f of x minus f of c all over x minus c. And when is it that this constant can come through the sine function? Well, if this limit exists and is finite, this was one of the famous limit properties. I think it was called pull the constant. I think that's what we called it. That becomes k times the limit as x goes to c of f of x minus f of c all over k minus c. This is at the heart of why you can do that, because we had pull the constants. If this part is finite and it exists, which it doesn't always, but if it does, pulling the constant is okay. By the way, all the properties are no good if the limits don't exist. They're obviously only good when the limits exist. Alright, so we continue with this. This becomes equal to your k. I'll make it in red. And that becomes k times this piece right here, which of course is f prime of c. I told you, so k f of c prime, I use the definition, use some careful steps here using the definition, use the famous property, pull the constant, and you get that it's k times the f of c. And if you want to emphasize it, look at the derivative business stayed inside here for the function. You keep the k out of it. That's exactly the principle. Okay? And such as this principle, pulling the constant, it should remind you of a lot of other different properties. When we did limits, there was limit of the sum, limit of the product, limit of the quotient, blah, blah, blah. When we did continuous functions, a constant times continuous is continuous. The sum of continuous plus continuous is continuous. The product, all these, they have the same theme, and so you would expect the same sort of theme in this part of the lecture. For example, what happens when you have the sum of functions and you wanted to take the derivative? This is exactly as you would expect it to be. You would do each derivative piecewise separately, and then you would add them up. Meaning that the sum of the derivative of the sum is the sum of the derivatives. No big surprise here. Let's see how you would actually apply it. Suppose you have the sum of two things, like a polynomial such as this. The principle tells you that to do the sum of the functions, to find the derivative, all you do is do each piece separately. So you handle this piece separately. That piece would be 3x squared, and then you would handle this piece separately. That would be 7x to the 6, and then you're done. Yippee-ki-yay. That hardly merits a yippee-ki-yay. Really, this is so easy. I gotta take that back. I take no yippee-ki-yay. This is way too easy. Want to step it up a notch or two? What if you had a different sum of polynomials? Well, yeah, this is, you just do each piece separately. This would be 4x to the third, and you're done with that piece, and then you go 8x to the 7th. Of course, I'm bringing the 8 down, subtracting 1. No yippee-ki-yay here. That's too easy. What if you had the sum of 3 or 4 different things? Still the same thing. You just do each piece separately. I would handle this piece separately. Well, this one mixes it up a little. You've got the sum of a bunch of them, and you've got constants on them. So let's do it. 3 times 4, that's 12x, and then you subtract 1, that would give you 3. 2 times 5, that would give you 10x, and then you subtract 1 from the x, that would give you 4. The derivative of x is famous, it's 1. You should add that to your list of famous ones if you haven't done already a million times for homework. And the derivative of a constant is well known to be 0. So the grand total would be 12x to the third plus 10x to the fourth plus 1. And we've done something amazingly simple and yet amazingly complicated. This is a formula, a recipe that at any given point would tell you the slope of the tangent line for this graph. Just picture, if you would, that graph probably looks something like this. That's probably what that graph looks like, more or less. And this little machine here, at any given point, you choose whatever point you want. X equals 7, boom. You plug that in there, it will tell you exactly the slope at that point. It's beautiful and yet simple to do. I did this just, I don't think it's good to lose track of what we're doing. These are all derivatives of functions, and we want to make sure we don't forget our past. Again, you got the derivative of a sum of a few pieces. All you do is each piece separately. So the derivative of x, well, that would just be 1. The derivative of sine is famously cosine of x. I love that proof. You guys remember when we proved that? You remember. The derivative of sine is cosine, and so nothing new there. I'm getting tired of these. Maybe we do one more, and then we got to switch it up a little. Okay, maybe I do 2 more. The derivative, if you have 3 things, the derivative of x is 1, the derivative of sine is cosine x, plus the derivative of ln x is 1 over x. Done. How about this one? It's not that different. All these are power rules. 3 times 6 is 18x, and you subtract 1 square. It would be a half x. We've done this one before. Negative 1/2 minus. The only difference is that it's the difference, and it shouldn't matter. The principle is still the same. Sum or difference wouldn't change, wouldn't make a difference. You just do each piece separate. That was a little pun. 5 1 over x. Then you're done. See how easy that is? Alright, enough of that. Let's change it to a product. Let's get a little freaky here. The product is amazingly different than all the other ones. If you're a novice, if you're a beginner, you might think that if you have g and then you have f and you wanted to take the derivative, you might think that, well, you might think that, whoa. Take it easy. Alright, so let me backtrack just 2 seconds. If you're a beginner, you might think that if you wanted to take the derivative of this, all you would do is take the derivative of the first and then the derivative of the second. But I want to warn you that this is one case where what you might think works actually does not. It's not like that at all. It's actually a little bit more interesting than that, and thank God, because I was getting a little tired of the other ones. This one adds a little bit more interesting ideas. Just to keep your mind interested in something. So the way the product works goes like this. What you do is let me do that again. Let's see if we can backtrack. Here, try this. Here's the way it works. If you wanted to take, if you have g of x times f of x, and you wanted to take the derivative of this, here's one way to handle it, okay? What you do is you write it again, g of x times f of x, and then you write it again, g of x times f of x, and you write it with a plus in the middle. And then here's the crazy thing, not crazy, but perhaps unanticipated thing. On the first one you take the derivative, and on the other one you take the derivative. That right there, that's famous. It's called the product rule. The derivative of the product is equal to the derivative of the first times the second plus the second times the derivative of the first. You got that? The derivative of the product is the derivative of the first times the second plus the first times the derivative of the second. Just like that. And here I've written it with better colors here. Exactly what would that mean for an actual example? Suppose you wanted to find the derivative of x times ln x. Let's go with white. Keep it consistent. X times ln x. You see, I've got trying to make the colors nice. I've got the product of 2 things, the x and the ln x. Here's what we're going to do. What I suggest you do is you write it all over again. X ln x, and then you write it all over again. X ln x. Okay? And then you write a plus in the middle. And if you stop there, you're going to get it wrong. What you got to do after that then is you say to yourself, hey, on this one I'll take the derivative of that one, and on the other one I'll take the derivative of the other one. And now you're in good shape. This is famous. This is world known. Everybody who is somebody knows the product rule. And then you just get to it and you do it. The derivative of x is 1 times ln x plus x times The derivative of ln x, well, that would be 1 over x. And so you get that this is equal to ln x plus 1. Just like that. Beautiful, huh? Just follow that. Let's do it again. Let's do it on an actual on a polynomial. Yeah, I should have done this. Let me switch it up a little bit to show you where those things came from. So one way to do it is the following. You write it x to the third times x squared, and then you write the same thing over again, x to the third times x squared, and then you write a plus in the middle. Right? Exactly the same thing written a couple times. Okay? And then you go on and you slap some derivatives. On this one you put a derivative on the first one, and on the other one you put a derivative on the second one. And that's a good setup. That's called the product rule. The next step is just you do each piece separately. The derivative of x to the third, well, that would be 3x squared times x squared plus x to the third times 2x. Right? That's this piece. That's the derivative piece, and that's the derivative piece here. And then you can clean it up some more if you wanted to. Why wouldn't you? We could clean that up a little bit. That would give us, let me think, that would give us 3x to the fourth plus 2x to the fourth. And of course you could even clean it up some more. That would give us 5x to the fourths. That would be perfect. This is a perfect way to practice a product rule. And of course we're going to have millions of homework assignments. You got to be so good with the product rule. It's got to be like walking, that easy, where you don't even think about it. As easy as walking or breathing. Of course, there's something interesting on this problem. This is a good way to practice a product rule, but perhaps not a good way to take that derivative. That derivative is x to the third times x squared. The derivative of that, really you could have just done x to the fifth prime, right? Isn't that the same thing? Isn't that x to the fifth the derivative of? Yeah, that's the same thing. And so you could have just used product rule. You bring down the 5x to the fourth. Of course, using the power rule. And of course, if you do it this way, you won't practice a product rule. So that's why I thought it'd be fun to do it both ways. Using a famous property that we've already learned, and practicing the product rule. Both lead you to exactly the same solution, 5x to the fourth. Nice, huh? Here's a little bit more interesting one. 5x to the third sine x. What you do is you write it all over again. 5x to the third sine x, 5x to the third sine x. On the first one you take the prime on the first one. On the second one you take the prime on the second one. Right? And then that's the product rule. And then the rest of it is not that hard. You just do each piece separately. 3 times 5 would be 15x squared sine x plus 5x to the third. The derivative of sine is cosine x. And you're done. Okay? That almost merits a yippee-ki-yay. Not really. Product rules. This is so easy. Of course, you could do that all day long, and you should do that all day long for homework. But that, after you get the hang of it, after you do 100 or 200 of them, it becomes really, really simple, and not even that challenging for you as a gifted human being with the ability to think. It becomes really, really monotonous. And so the next high that you want to get is the next quest your mind would be pointing towards is why. You would want to try to understand why. Why is that weird thing? What's going on here? The derivative of the product is you have to write it over again, and then you have to take the derivative of the first and then take the derivative of the second. Why? This would be probably the most interesting thing. Once you learn how to do the rule, the next thing you should be asking is why? Why? And that, my friends, that's an interesting question. So let's see if we can take a stab at it, okay? All right, what a privilege to share the calculus story with you guys. All right, here's another chapter of the calculus story. It's an honor to be here. Let's get rolling here. Last time we talked about some big ideas. The big idea was called the derivative. The derivative is a formula, a template to give you all the possible tangent slopes at any given point. See when such a thing exists, and we cooked it up in a really nice way. We started off with just a secant slope, which is pretty ordinary, change of y over change of x. Then we did something magical to it. We slapped a limit on both sides, moving the x closer to whatever point you want, and that turns, it morphs, it evolves the secant slope, it turns it into exactly a tangent slope. And so we got this really nice definition for the ages, definition of a derivative. There's actually two famous ones. There's another one called involving an h, but I think although they're equivalent, I like this one better. I think the other one I'll delegate to the homework assignments. Has a less beautiful one in my point of view. So anyways, we did this a whole bunch, and then the name of the game was for you to do it about a gazillion times for homework. For all possible functions that you've met in your life, you always want to go around asking, hey, what's your derivative? E to the x, hey, what's your derivative? Ln x, what's your derivative? Log 3x, what's your derivative? All the functions that you ever met, we want to know what their derivative is. And we've already accumulated quite a little list of derivatives that we know. Many of these we've done already. We've even observed some major patterns here for the ones that can be expressed as a power. This one can be expressed as x to the 1/2. We have the famous power rule. And the game, this is more or less what we did last time. We want to add some more. Maybe you did a lot of these for homework. These are incredibly important. These are also, they should go on the list of famous things. And then what we want to do today is we want to keep adding to that more derivatives of everything that you ever thought about. And now we want to start adding a couple more little ingredients in there. These other ingredients that we want to start adding are called derivative properties. And these will help you find even more derivatives. With the next week, this week, by the end of this week, you'll be a master, you'll be a black belt of derivatives. That's the goal. And so that for today, there's not a lot of major ideas per se. There's only maybe one or two major ideas, but it's a major day because we want to make progress in this quest to become masters at derivatives. So we'll add a couple maybe new ones, but more importantly, we're gonna dwell on these ones. These are called derivative properties. With these, we'll make a lot of new ones. Okay, that's the day today. So let's think about the first property. This is called a derivative property. It goes like this: every time you've got a constant, say k, any constant, 5, 7, 3, times some function. This function could be anything. X to the third, it could be sine x, it could be e to the x, any sort of function, or even another constant. If you have a constant times function, and this little prime thing means take the derivative of, this means find the machine that gives you all the tangent slopes. The amazing thing is, or the interesting thing is, maybe not that interesting, but the expected thing is exactly what happens here. You could actually take this k and put it outside of these and don't even worry about it. Find the parentheses of the function f of x and then worry about the k later. You can keep that out of the derivative business, find out what that is, and then multiply by the constant. It's a famous property for constants, and I can express it this way. This is equal to the constant times f prime of x. This is expressing the fact that you could take the constant out of it and just worry about the derivative of the function inside. That's what this is expressing. Talk is cheap. Let's actually do it. Suppose you have, we've already done x to the 4th. That we've done before. It's 4x to the 3rd. Or you've done it for homework. You've done it a million times. Here we're contemplating the question: what happens if you have a constant times that? And what I'm saying is, you know what? We could just keep the constant out of it. Keep it out of the derivative business and proceed with the regular stuff. So this would be equal to 3 times, I'll deal with the derivative in here. The derivative of x to the 4th is equal to 4x to the 3rd. See that takes care of the derivative, and then at the end of that we will have equals to 3 times 4 times x to the 3rd. Of course that's equal to 12 x to the thirds. This is called pulling the constant. And in practice, this goes by much quicker. If you have 3x to the fourth and you got to take the derivative of that, you think, well, that's 4 times 3, that's 12x, and you just leave the 3 there. That's usually how it's done in practice. But the principle behind that is, of course, the idea that you could take the constant out. Want to try it again? So we'll do it slowly because we're beginners here. Take out the 7 and keep that out of the question here. Keep that 7 out of the derivative business. You just deal with the derivative in here. The derivative, you should read it this way. This is a parentheses. The derivative of whatever's inside the parentheses. Derivative of x squared, that's one of the first ones we ever did. If you recall, that was famously 2 times x. And so the grand total, of course, would be equal to 14x. And again, in practice, it goes by much more like this. If you had to take the derivative of that, you go 2 times 7 is 14 times x, times, I gotta do Control Z. Whoa, take it easy. Don't worry, I got this. I got this. Maybe not.